Okay. So this week will be all about this so-called approach of divide and conquer. But let me relate it to, all these things we've been repeating. Two big generic themes in the class again is one, trying to identify good subproblems to break problems down to size. This is sort of like a code word for recursion and induction, which are more or less the same thing for us. And then there's this other issue of taking some of the nice algorithms we already have and figuring out how to use them in creative ways by changing the input. That also leads to surprising conclusions on the negative side, suggesting we can't solve some problems as well. But today's discussion will probably mostly fall in the first category of trying to identify subproblems and break problems down. Okay, but there will be some difference. So we've seen, which sort of within this umbrella of identifying subproblems, there's at least two different kind of subcategories. One is what we first did the first day was merge sort, which at some level I think everyone had seen once before. But there, we're taking a lot of elements, we're dividing in half, sorting the halves separately, putting it back together. That was sort of the famous or canonical example, introductory example of the divide and conquer algorithm. But a different kind of identifying subproblems, or one with sort of different emphasis, is this dynamic programming, which is really what we spent more time on over the first few weeks. And the example I have up here is, for example, the longest increasing subsequence problem, which we've solved and we solved various variations of, which was a trickier problem, I would think, than sorting. And really the hardest part was identifying the subproblem. Let me open this up a little more. So, okay, how did merge sort of decompose its subproblems, right? So at the top we start with some unsorted array. So here everything in black is sort of unsorted, and then it eventually starts to get sorted and turns into red. So at the top we have an unsorted array. We keep dividing in half, dividing in half, dividing in half. If you actually were to unroll the whole recursion. Right, until we get down to a base case of one or two elements. I guess here I use 2 as a base case. It's very easy to sort 2 elements. That's when we go from black to red. And then we start merging things together, leveraging the fact that 2 already sorted sequences are very easy to combine. Much easier than sorting originally. We can merge 2 sorted sequences in linear time. And so we start to kind of put things back together. So this is supposed to be sort of a diagram of sort of the dependencies of the subproblems as they relate to one another. By contrast, I tried to draw something similar or analogous for longest increasing subsequence. So here I'm using a formulation where the sentence is LIS of I is the longest increasing subsequence of the subarray starting at I, including AI. Of course, there's different ways to do it, but that's the one I've chosen here. And each subproblem corresponds to a suffix of our input. Okay, so I've kind of drawn the first subproblem, second subproblem, third problem, as many would fit. I guess that was 8. Okay. And, compared to merge sort from before, our problems are very highly overlapping. Right? Each subproblem only takes off one thing, which in the algorithm was just kind of guessing one choice. And there was a lot of dependencies, right? So in this, if you guys remember how this one was implemented, one subproblem would check, sort of all the valid subproblems, which could be many of them, depending on whether the leading number was big enough. Okay. So to put these two paradigms side by side, and trying to understand on one hand why they're similar, on the other hand why they're a little different, and why maybe one is better for one case than the other. So with sort of divide and conquer type algorithms, you're going to see in general fewer subproblems, much more selective about the subproblems, and it's going to be much more disjoint. There's going to be an effort to keep the subproblems disjoint. Whereas with dynamic programming, usually these were tricky problems, and the goal was just to get any polynomial running time. They weren't so aggressive about partitioning the input. They were more trying to be exhaustive to make sure you don't leave out any cases. So we get very overlapping subproblems, not trying to cut corners. Cutting corners rarely works. Showing that merge sort is relatively easy, I think, to separate sort. I mean, I think it's easier to digest for the first time and see why merge sort is correct. It also was never really a debate whether or not sorting was in polynomial time. Right, this is a problem that was already in polynomial time. We're just trying to make it faster. Whereas longest increasing subsequence and other dynamic programming problems are much more subtle to show why they're correct. And many of the problems, it's not obvious that they have a polynomial running time right away. You really have to come up with a good sentence, a good way to break down problems to unlock the polynomial running time. Okay, so, again, merge sort, very economical. Really hardly does the same thing twice. I guess on merge sort, it sort of looks at each number log n times, which is very little. Dynamic programming is, by contrast, very conservative. It's really not trying to leap to conclusions. It's sort of exhaustively saying, well, the solution has to do one thing or the other. Let's try both options. Check both options so we don't leave anything out. It's very conservative. The running times you see for divide and conquer are typically very fast. These are problems that usually it's not controversial whether or not they can be done in polynomial time. The only question is how fast can we make it. So merge sort is n log n. That's quite good. Okay. Sorry. Okay. So merge sort is quite fast. It's n log n. And we'll see, I think all the divide and conquer algorithms we have are going to be close to n, which is very good. There are, of course, exceptions to this, but by and large, you're taking a situation where it's not very controversial that there is a polynomial time algorithm. The only question is, can you be more clever and do things faster? The dynamic programming algorithms generally or often have larger polynomials. Longest increasing subsequence was n squared. Most of our problems were probably n squared, n cubed, something like that. Maybe sometimes you can go from n cubed to n squared if you're clever. We had one or two examples that might have been closer. I don't know if we had any n's, n timelines. But anyway, usually the emphasis on dynamic programming was getting any polynomial running time. Of course, the smaller the better. And usually we didn't get anything close to n. In the back, yeah.
Wasn't there like something on trees that was running in n time?
Oh, that's true. Things on trees could be really fast, yeah. And things on DAGs could be really fast. That's true. That's absolutely true. Yeah, okay, good. I didn't think of that example this morning. We did have some exceptionally fast ones in terms of graphs. Especially sparse graphs. Okay, so that's sort of where our discussions this week will lie. The emphasis is not so much on proving something is polynomial at all, but trying to make it really a fast polynomial like sorting or whatever. Yeah. All right, so I'm planning to discuss 4 famous examples. integer multiplication, selection, a geometric problem involving kind of finding the two closest points to one another, and a very broadly impactful tool called Fourier transforms. Number 4 might be the most useful in reality, but it's also the most kind of heavy probably. But we'll start with integer multiplication, in part because we understand integers very well, so it's a good starting example, I think. Okay, so let me explain the setup. Okay, so simple problem. You want to multiply two n-bit integers. So think of n as being large. You're multiplying two very large integers. Okay? And you want to do it as fast as possible. Okay. I guess the product always has at most two n bits, unless I'm mistaken. Okay, so so when we multiply two numbers, for example, I don't know, 1, 2, 3. Okay. How did we learn how to do this in school? Well, what I was taught was something like this. It's sort of like some kind of table-looking thing, right? And then here's where I'll embarrass myself, but I think this will be like 18. You carry to 1, you get 13. You carry to 1, you get 7. And then you go to that next one with the 5. 15, carry the 1, 11. Carry to 1, 6. And then lastly, what did we get? We get like 12, and then 9, and then 4. And then, guess we add them all up. Okay, so like 95% chance I did that correctly. Okay, that's how I was taught to multiply numbers. That's an algorithm. I did it in decimal for kind of, that's what we're used to doing, but it could also be in binary, right? So I'm just making up numbers. If I wanted to multiply 1011, that would be, what would that be? I think that's 11. Okay. And then what's 1110? 14. Okay. So we're multiplying 11 times 14. But the point is that we can do the same thing, only when we carry, it's at 2 instead of 10. Okay, so this is all zeros. I guess it's kind of much simpler with ones and zeros now that I do it. Okay. 1101 and 1. This is great. We should do it always in binary. Okay, 0, 1. This is a 0 and I carry the 1. So I get 3. So that's a 1 and I carry the 1. It's kind of confusing. Carry the 1. Get another 1 and I carry the 1. I get a 0 and I carry the 1. 0, 1. Okay, so hopefully we did that correctly. What is 1, 0, 0, 1, 1, 0, 1, 0? 2 plus 8 plus 16 plus 128. Anyone?
I think it's 152.
154. 152, okay. Hopefully it's either 152 or 154. Okay, so whatever. The point is that this binary thing is not a big deal. How long this tabular approach as a function of the number of bits roughly take? Yeah.
N squared.
N squared. So we see that we're sort of multiplying everything, right? And we're kind of looking at all pairs of digits from above and below. Okay. So the only question is, can we do better than n squared as a function of the number of bits? Okay. All right, usually when I teach this, somebody eventually objects and say, why do I care about multiplying integers when everything's fixed width anyway? And it's accelerated by CPUs if you're doing 32-bit or 64-bit integers. Of course, it would only be interesting for very large integers. Okay. One is just because we already know everything about integers, so it's a good example to learn with. But there's some historical significance too. Sort of, in the very early days of thinking about algorithms in the 1950s, presumably we knew everything we knew there is to know about integers. So a very famous mathematician named Kolmogorov was going around saying, oh, there should be a lower bound of n squared for integer multiplication. So Kolmogorov's a big guy. He invented probability theory, among other things. But then someone very young, probably a graduate student, came along and showed how to do it in n log n time in 1960. So that person's name last name is Karatsuba, which was sort of where everyone's sort of dumbstruck. Like, okay, we've been multiplying numbers for a long time. No one tried to do it differently. But it also suggests that maybe there's many other things, kind of obvious, seemingly obvious things we take for granted. Maybe matrix multiplication is another example. Multiplying polynomials will come up later this week. Where sort of the obvious way, the way we always do it by hand, is not necessarily the best algorithm. And sort of made algorithms interesting. We didn't think there was anything interesting to do with some of these mathematical objects that we've long taken for granted. Okay, so that's the best cell I have. Okay, so divide and conquer. Divide should show up somewhere. And we're going to think about dividing the bits in half. Okay, so let me take x, which has n bits, and split it into two bit strings where one represents the biggest bits, the most significant bits. The other one represents the least significant bits. Here I'm just assuming n is even to make things simple. Otherwise, you can add a 0 or a 1, add a 0 at the beginning. Okay. So x can be written as x1 bit shifted n over 2 times plus x2, where x1 and x2 both have n over 2 bits. Likewise, we'll break down y. Okay. All right, so this is just some notation to split things in half. But in terms of this notation, we have, in general, we have x times y. The part I didn't write would have been substituting in times y1 times 2 to the n over 2, plus y2. And if you expand this out, we get 4 products of our smaller bit strings. Okay, so we have x1 times y1 plus x1, the cross pairs, x1 times y2 plus y1 times x2 plus x2 times y2. Okay. We haven't really done anything interesting yet. Okay, so we have sort of taken one multiply of 2 n-bit strings and turned it into 4 multiplies of n over 2 bit strings. Okay. And so you would get a running time, if you have plugged this in, of something like t of n is equal to 4 times t of n over 2 plus big O of n. And when you do the kind of recursion tree, right? Oops, sorry, n over 2. Okay, you get total work n on the first level, but then 2n on the second level, and you've kept going as 4n, 8n, so forth. There'll be a geometrically increasing sequence doubling each time. And at the bottom, it's all going to add up to n squared. So this has done really nothing as far as making things faster go. Dividing it up into 4 at half the size just gives you the n squared running time again. Okay, so we haven't done any tricks yet. Okay. All right, so let's look at this product. x1 plus x2 times y1 plus y2. Okay. So if I just do things the old-fashioned way, and what do I miss? Okay, so for some reason I've taken x1 plus x2 and multiplied it with y1 plus y2. That's sort of a weird thing to do because you're kind of taking the 2 bit strings and you're adding them on top of each other and then you're multiplying. Okay. Still, let's look at this product, right? And okay, so what's great about this? Okay. Yeah, let me open up the floor. So, okay, let's look at these terms on the right-hand side. And here's sort of that calculation we had just done. What are some coincidences or some observations, anything, shout them out, between the top and the bottom?
They have all the same variables.
Oh, okay, so we have, so we start having this, okay, so this is this, right? And this is this. And these two are these two. So it sort of captures everything. Okay, so there's this correspondence. Okay. All right, so I only have one chance to ask you guys before I explain his trick, so I might at least try. How might I take advantage of sort of these algebraic coincidences? Yeah.
Maybe we could split them further from x1, y1 and do the trick again, and then we could look for repeating like 1s and 0s.
Okay, maybe we can split x1, y1 further and do the trick again. I don't know if that wouldn't work, but I feel like we'll just keep pushing the question down and never quite answer it. No, we're not going to you sort of, everything you need is already there. So there's nothing left to. The issue before was, let me frame it maybe more suggestively. The issue before was we had taken one multiplication and turned it into 4 multiplications of n over 2 bits. It would be amazing if I could turn into 3 multiplications of n over 2 bits. So my question then is, sort of naively we had 4. Then I gave you sort of this identity. How can we sort of use that in some tricky fashion? Addition and subtraction is relatively free, right? Because addition and subtraction takes linear time. So don't worry about it. You can add and subtract basically all you want. Yeah.
I guess if you add before you multiply the 2, so like add x1 to x2.
Yeah, so you can, sorry. What did I mean? So you have plenty of time to add these together. That's going to only be linear time. And we're fighting n squared, so it's pretty safe. Okay, so I tell you, you've already added together. I guess I should have drawn the squares separately. Okay, let's say you've also added those together. I'm looking for a trick where roughly I want to simulate that top line by using only 3 multiplications. Yeah.
Would you be able to add the ones inside the parentheses, x1, y2, and y1, x2 together, and then?
You could, but you would have to multiply those two first. So you've paid 2 multiplications. Another way to try to set up this question is at some level on this picture there's 5 different choices of pairwise multiplications drawn up there. There's the 4 original ones plus the 1 on the left. Can we use just 3 of them to recover the original 4? Yeah.
So I can't figure out how to make this work, but is there some kind of completing the square thing you could do?
Yeah, is there some kind of, I'm not 100%, yeah, is there some kind of completing the square thing you can do? I'm never quite sure what it means. Well, at some level, I guess maybe that could be considered ish.
Well, I'm just thinking because if you can turn it into a squaring operation and the middle is actually 1 multiplication times 2.
Okay, so I think in that specific sense, the answer might be no. But I think it's in the kind of the right sort of mind frame. Yeah.
You can write the middle term x1, y2 plus y1, x2 in terms of xy, x1, y1, and x2.
Okay, so, okay. All right, so here's the 3 we're going to use. We're going to multiply these 2. We're going to multiply these 2. Okay. And then I'm also going to multiply this bigger one on the left. Okay. And if I have those 3, then I can recover this middle term. Okay. So we can rewrite x2, y1 plus x1, y2 is equal to x1 plus x2, y1 plus y2, minus x1, y1 minus x2, y2. Okay. This is very much like a computer scientist answer to the question. A mathematician would never care about this kind of thing, right? But we're kind of using memory. We're saving an answer and reusing it in a clever way. Okay. So we only actually have to do 3 products this way, distinct products, and then we just do some adding and subtracting, which is fast compared to the n squared that we're fighting against. Okay, so that's the trick. All right, so when we set up one of these divide and conquer things as a recursive algorithm, we basically do the same steps as before. Some things naturally change. But we should make clear what the function is that we're implementing so that when we use it in a recursive call, we know exactly what we're getting. Okay? The clearer the sentence, basically, the more easy. The proof is almost immediate. We implement exactly what we said we're going to do. Okay? If there's a difference, we should relate our recursive algorithm to the original problem. That was often the case for dynamic programming. For the problems we discussed this week, it's usually kind of obvious. Like merge sort, you just sort the whole input. It's not like that different than the original question. We'll analyze the running time, of course. This time we'll do it differently. This time we'll often use recursion trees and stuff like that. Before it was sort of this count the problems, time per problem kind of thing. And before, we did have to note that we were using caching and saving answers to get that running time. And then, we should still prove it's correct, although in general that's almost like just repeating the recursive spec over and over again. As long as that's made clear, that's basically your induction hypothesis. It's what you assume from the smaller problems. Okay. So just to develop good habits, here I wrote some sentence. I defined some function called multiply. It's taking 2 bit strings of n bits, and it returns their product as a 2n bit array. Okay, and so of course that's exactly the problem. Not saying much, although it does clarify. I think the most important thing is that it clarifies what I'm getting when I use it as a subproblem. Okay. And so here I've implemented what we've discussed. This is a little bit gory. Okay, so let me first, here's 2 base cases. They're not so interesting, 0 and 1 bit. Okay. Here I'm just padding a 0 if it's not even. Sorry. Where the hell is it? Okay. I'm padding a 0 to make it even, just so I don't have to write like n over 2 up and n over 2 down up everywhere. We split it in half. Okay. And here are the recursive calls. Okay, so we have x1. Okay, this always happens. Okay, so there's the first half, second half, first half, second half. Okay. Here is x3 is taking x1 and x2, adding it together. I was just being kind of verbose to be clear. Y3 is adding y1 and y2 together. One very minor technical point to make is that when you add up 2 n-bit integers, or I guess, you get an n plus 1 bit integer because you might carry the 1. So technically that third recursive call is actually adding 1 more bit, but that won't really change the running time. Okay, because 1 is very small compared to n. And then here are my 3 recursive calls. I multiply the leading bits, I multiply the least significant bits, and then I do that funny multiply where I'm multiplying the sum. And then, you bit shift. And then here's that subtraction from that identity. Bit shift appropriately. And then the least significant bit. So bit shifting is just going to take n time. It's not really a multiplication. It's just written to look like a multiplication, but make some mathematical sense. Okay. All right, I don't think this algorithm has any surprises, sort of exactly as we had discussed. Okay. All right. So as far as the running time goes, though, this is linear time, this is linear time, and really the only issue is my 3 recursive calls, which is roughly n over 2, but maybe adds 2. Maybe adds 1 bit from rounding up an odd number, or from adding a bit when forming the sum, x1 plus x2. Okay. So I only mention, it's a little bit technical, and I wrote it more slowly in the notes. But, the first time we write the recurrence, we might, instead of writing it this clean version, okay, maybe we should account for that 1 extra bit, right? It's a little bit messier, n over 2 plus 1. Okay? The moral of the story is that this really doesn't matter. Okay, and there's some transformation you can do, and just assume n over 2, which is much cleaner when we do the recurrence tree. Yeah?
Is that true for all recurrent calls that have a false constant in them, or only for this
I cannot think of an exception. And, but I also worked out, okay, so here's what you do. Okay, so let me, sketch out the high-level ideas, just so that if you wanted to read that page in the notes, it'll come more quickly. Okay? So if I was being really technical or really careful, I would have first written this. This would have been conservative. Okay? Now, I would prefer a nicer version, which we'll analyze in a moment, would be 3n/2 plus big O of n. Right? Because in my recurrence tree, I'm just going down by half every time, and that's much easier to think about. Okay? Now, what you can do is we can define S of n to be Tn plus alpha for some alpha to be determined. Okay? So that if I then plugged in S of n is equal to Tn plus alpha, I would get the nice recurrence. Okay? As it happens for this one, if you had set S of n is equal to T of n plus 4/3, or 3/4, but I think 4/3, if I took this, so I define S of n to be T of n is equal to T of n plus 4/3, and I had substituted into here, I would get the nice recurrence. Okay? But there's also a mechanical way of, if I want to get the nice recurrence, how do I choose a nice alpha? You just kind of write down things, you make two things equal and say, oh, you should choose alpha to be 4/3, and then life is good. Okay? As far as I can tell, it's completely generic, but I guess to do it correctly, I would look at a generic recurrence where instead of 3 times Tn/2, I would write alpha times T, or I would use alpha beta times T times gamma n plus, stuff, and work it out. This, as far as I can tell, this detail had not actually come up in any other algorithm we've done before, partly because in merge sort we can just assume it's a power of 2 by a different trick. Okay. I think that the right moral way to look at it, though, is that we're really concerned with T of n when n is really big. And we're interested in the asymptotic rates growing in n. And we really shouldn't be distinguishing the difference between n and n plus 1 anyway. Okay. Anyway, so as far as like homework goes, just write the simple one. Maybe make a comment that you're omitting a plus or minus 1 or something. And say, it doesn't affect the running time. You can double check if you want. Okay. Other textbooks I saw were like, it's basically Tn/2. they just stopped. Okay. All right. So anyway, so that plus 1 bit is not a big deal. In general, recurrences, don't get too distracted by n plus 1, n plus 2. Focus on n. Okay. All right. So, so what would a recurrence tree look like? We have, input of size n at the top, and I do n work. And then we have 3 subproblems of size n/2. Okay. And then I have, 9 subproblems of size n/4. And so forth. So this will give me 3n/2. This will give me 9n/4. But in general, if I'm looking at the ith level, what would be the work per level? What's kind of the pattern? Okay, so every time it's going up by a factor of 3/2. So the geometrically increasing sequence. Okay. What's the height of the tree? How many levels till we get to the base case? I heard log base 2 and log 3n. Log 3 because, 3 is suggestive because of 3 branches, but then why log 2?
Because each branch is n over 2 at the last one.
Yeah, okay, so we can look at, there's 2 numbers floating out there. One is how many branches, the other is how much the input's going down by. But for this, we're actually interested in how long it takes for the input to get to 1. So we're interested in how much the input goes down by. So that's why it's log 2 rather than log 3. Okay. And the only time you get interesting running times is when, log 2 of n, let me write that, is when the amount is going down is different than a branch factor. Then you either get geometrically increasing or decreasing sequences. Okay, so if you have a geometrically increasing sequence, you're just trying to estimate the sum, then there's a shortcut. What's the shortcut? So another example of a geometrically increasing sequence is like 2 plus 4 plus 8 plus 16, right? That's factors of 2. And you know it's always going to look basically like the largest term. Right? 1 plus 2 plus 4 plus 8 plus 16 is 31. That's within a factor of 2 of 16. If I added 32, we get up to 63. That's within a factor of 2 of 32. So every time with the geometric increasing sequence, it's going to be dominated by a largest term, at least when that coefficient is a constant, like 3/2, like 2, like 1.1. Okay, so this is going to be the height of the tree, again times n. How do I chip away at this? Well, you can do a couple different things. But one you can do is you can write 3/2 as 2 to the log 2 of 3/2 times log n. Okay. And you can reverse it. If I reverse these two, and then 2 to the log 2n gives me n. I'm sure there's more slick ways to do it, but I never remember. Okay. Meanwhile, log 2, 3/2. But remember, a division becomes a subtraction. Okay. Log 2 base of 3 is some annoying number. But what's log base 2 of 2? 1. So this is equal to log base 2 of 1 minus 1. And so in that coefficient, this minus 1 is going to cancel out with this n. Yeah?
Isn't it log base 2 of 3?
Yes. But the minus 1 kind of sitting in that exponent will cancel out with that n that was sitting the whole time, since n is n to the 1. Okay, n to the log base 2 of 3. Now that's better than n squared because n squared is log base 2 of 4. This is log base 2 of 3. That's always better. But then if you ask Google, then it is something like n to the 1.585 or something like this. Okay, so you can do better than n squared for multiplying integers. Again, you may never be multiplying big enough integers to actually need this, but it's surprising, and it demonstrates the effectiveness of this technique. Does anyone know what the world record is? Probably not. Anyone want to guess? So you can do n log n, and that was only established a few years ago. Before that, it was like n log n, log n, or something annoying. And I think it's randomized. I think it's really complicated. And I think it's really based on this Fourier transform idea that we'll talk about Thursday. it takes the Fourier transform idea, and then that's only the beginning. But it showed up in the biggest math journal recently. Okay. All right, that's so much for multiplying integers. Let's talk about selection in the remaining time. Okay. So I give you an array of, say, numbers, but in general comparable elements, add in elements. And I ask for the case biggest one. Or maybe a simple case, I ask for the median of this array. The easiest thing to do, of course, is to sort the array and then pick out the median. So you can do n log n. So there's no debate that this is in polynomial time. The only question is, can you do better? Another question that, like multiplying integers, would seem to be so simple that we know everything about it. Okay, so we're going to make a recursive algorithm. Again, just developing habits. All I've done is define what I want my function to do. So I'm calling it select. It takes as input k in an array, returns the kth smallest element in the array. All right, so I'm going to do a couple thought experiments to gradually unroll the idea of the algorithm. So the basic idea is that to divide, we're going to try to pick pivots. A pivot is just one number out of the array, but what are we going to use it for? I'm going to use that number, and I'm roughly going to kind of divide the input in terms of what's smaller and what's bigger. And then I'll say, oh, is k on this side or that side? Or is maybe k equal to the pivot, and I'll recurse appropriately. But we'll do that in increasing sophistication. First, what we're going to do is a thought experiment. A special case of this selection problem is finding the median. But let's just pretend we can find the median linear time. Okay? So suppose just as a black box, I give you a subroutine called median, which will return the n over 2 rounded up element in the array. Okay? Of course, that's a special case of what we want to implement. But it's still kind of interesting to ask if the special case can be used to make the general case really fast. And then we'll figure out how to deal with the special case. Okay, so fine. So the algorithm we're going to look at first then will be as follows. I'll take my large array. This is just the base case, not so interesting. So I'm going to use my black box and I'll get the median out of my array. Okay. Now, if it turns out I was looking for the median, like k is equal to n over 2, then I'm just done. That's great. But the more interesting case is when k is bigger than n over 2 or k is less than n over 2. In which case, I want to recurse. Okay. Now, if k is bigger than n over 2, right, so I kind of have k, and then here's all my elements bigger. Sorry. Here's my pivot p, which has rank n over 2. And here's all my elements bigger than p, all my elements smaller than p. If k is bigger than n over 2, then I should go on the right-hand side and look for the element in there. The right-hand side is still unsorted, but I know it's amongst them. Okay. So here, again, it's a little bit wordy just to be conservative. But I'm assembling... Oh, I got it backwards. Okay. Okay, if k is less than n over 2, then I should assemble all the elements that are smaller than the pivot. I'm not sorting them, I'm just filling out a new array in whatever order. And then I'm going to recurse on that side. Okay. Otherwise, if I'm looking for something that's more than the median, bigger than the median, then let me build the array of everything that's bigger, and then recurse. The only thing to remember is that I'm omitting the first n over 2 elements. So if I was looking for element 100 and I've removed 50, I'm now looking for element 50 among the remaining. So I have to update the rank of the element I'm looking for. So that's why we have k minus n over 2. Okay. All right. So assuming that median takes linear time, how long would this overall algorithm take? So we can annotate the code. This would take linear time. This is a constant. This is a constant. I guess here I'm building an array that'll take me linear time. Although, yeah, rebuilding an array. And then I do a recursive call to n over 2 elements. Okay. And then the same thing down here, linear time, recursive call. And you only do one of the 2 calls, even though 2 are listed, of course, but there's an if-else statement. Okay, so we end up with something like this. Okay, pretty simple recurrence. You guys can probably eyeball this and tell me what the running time is. The recurrence tree wouldn't be very interesting. We have a problem of size n, problem size n over 2, problem size n over 4, all the way down to 1. The amount of work on this level is n over 2, n over 4, all the way down to 1. What does n plus n over 2 plus n over 4 plus all that add up to? Yeah. O of n. Just because in general, 1/2 plus 1/4 plus 1/8 plus 1/16, it never quite gets to 1. But in general, any geometric decreasing sequence, even ones not as nice as 1/2, sum to a constant. Maybe a bigger constant. If it was 2/3, it would be something closer to 3/2 or something. All right, so this would be extremely fast. This would be a linear time algorithm. But of course, we don't have access to the median. So as the next thought experiment, suppose I could only approximate the median. Suppose I had access to a magical black box that will return some element that's in the middle 80%. So it's not the smallest 10%, it's not the biggest 10%. It's in the middle 80%. Just approximating the median, but it's not too extreme. It's bounded away by some constant. 10% is sort of arbitrary. I could have chosen 1%, I could have chosen 30%, you'll get the same thing of the constant. Okay. Now, we can take the same algorithm and make that one change. Okay. So now instead of getting the exact median, I just call this thing that's going to give me approximately a median. Something within the middle 80% instead of exactly in the middle. One extra step we have to do is that before I always knew that pivot was right in the middle, so I already knew its rank. This time it could be some other number, so I do need to calculate what its rank is. It might be, if there's 100 numbers total, it might be number 11, it might be number 89, it might be number 50, but I still need to calculate it. So I can take that approximate median and compare it to everyone. That takes linear time. Right? I can see how many numbers are smaller, how many numbers are bigger. All right, so we do have to do a little bit of legwork to calculate what the rank turns out to be. If it's what we're looking for, then lucky us. Otherwise, did I do this correctly? Good. If the rank I'm looking for turns out to be less than the rank of this approximate median, I need to look at the smaller elements. So I assemble the smaller elements and I recurse. Or if the rank I'm looking for is bigger than the rank of this approximate median, then I should assemble all the bigger elements and recurse. Again, though, I'll update the rank in the subproblem. If I was originally looking for the 75th number, but the median had rank 50, I'm now looking at rank 25 or 24, depending on the fence post. I think 25, among the numbers bigger than the approximate median. I'm subtracting out 50 of them. Okay, so this is just perfectly matches what we previously did by making the natural adjustments when we get only an approximate median. Okay. All right. So now what does the running time come down to? Last time we had something like this. Okay. This time, though, we don't get 1/2. Okay, we get some number between 1/10 and 9/10, because we're guaranteed the median is not in the outer 1/10. And what's the worst case of those options? So the worst would be 9/10, right? But in the worst case, I'm at least getting rid of 10% of the input, even if the median was on an extreme of what was possible and the rank was the element we're looking for is on the other side. Okay. What is this running time? Recursion tree will look like n. 9n over 10. 9 over 10 squared times n, and so forth. Not too interesting. The work per level n, 9, 10 n, 9, 10 squared n, and so forth. In general, look like 9 over 10 to the I n. If I sum up all these powers of 9 over 10, what do I get? Seems more complicated. Yeah.
Would it be approximately like 10 over 9?
Yeah, and it's just a constant. It's a geometrically decreasing sequence. A bigger coefficient will give you a bigger constant, but it has nothing to do with n. That's my real concern. Whatever that constant is independent of the input size. Okay. So, yeah, it'll be something like 10 over 9 or maybe 10 over 9 times 10 over 9. But as an algorithmist, you're just saying decreasing geometric sequence, I'm in the clear. None of this will add up to anything significant. All right, so, okay. So now we know that a median, maybe it's less surprising that median would be really helpful. It splits the input in the middle. But even an approximate median, I just chose 1/10, but I could have chosen 1%, 1 over 100 or 1 over 1,000. We would have come to the same conclusion. An approximate median that's at least bounded away from the extremes by a constant percentage will give you a linear running time. Okay. So we've taken this original problem of this very precise problem, right? Add elements, find me the case one or case a variable. And we've turned it into a problem of out of n elements, give me something that's like vaguely close to a median, except it can be quite loose of an approximation. Okay, so I've taken sort of an exact problem, and with this divide and conquer framework, sort of now reduced it to what would hopefully be an easier problem. Okay. All right. So that's where this the real tricky idea comes in. This is a method for approximating the median quickly. Okay. Of course, this algorithm is famous because selection seems like a very basic problem that we want to do faster. But it's also kind of infamous because the authors that participated on this paper are almost like a Mount Rushmore of algorithm design. So that's, okay, there's out of 5 people, 4 of them are Turing Award winners. So Blum, Floyd, Rivest, and Tarjan are all Turing Award winners. So Blum and Rivest did a lot of cryptography stuff. Floyd was from Floyd Warshall, he did a lot of compiler stuff. And then Tarjan comes up every other lecture for us. Does anyone know anything about Pratt? Vaughan Pratt? Yeah.
Doesn't he have a pattern matching algorithm?
So he has a pattern, he has a lot of other algorithms. And he also is basically a founder of Sun Microsystems. Sun Microsystems came out of his research lab. So I don't know why he didn't get an award too, but is it just 5 very strong guys? Among other things, Pratt also showed that trying to figure out if a number is prime is in co-NP. Anyway, it's a big deal. Okay, so, okay. Don't know why it took so many people. All right, so what's the idea? So you start with your big array A. And what we're going to do is, just for simplicity, let's think of A as a multiple of 5. If it's off by a little, it's not a big deal. And we're going to divide it into chunks of 5. Okay? So here's one set of 5. There's 5 values in it. Okay? And out of those 5, I'll do a few comparisons and extract out the median of the 5. That'll take constant time for each set of 5. Okay? And so each of these green squares represents the median of a set of 5 in your input. Okay? Now, we take all those medians and put them into a new array. You've roughly decreased your input size by a factor of 5. So out of every 5 elements, you've taken out 1. Okay? And now we're going to try to find the median of your n over 5. So this is where the median of medians comes in. And we don't know how to do that, but the input's smaller, so we can recurse. So we're going to kind of reduce the input once by a constant factor by kind of breaking up into lots of small problems and stuff like that. And then I'll recurse on the smaller problem to find the median. Again, the median is a special case of select, so this is really recursively calling select. Okay. All right, so this is called the median of medians trick. Okay. And so the claim we'll now prove is that the pivot that's extracted from this method, the median of medians, is basically an approximate median. It's between 3n over 10 and 7n over 10. It's definitely between those two if it's exactly a multiple of 5. If it's not exactly a multiple of 5, okay, there's a little bit of kind of fence post error, so this should have really said something like plus 2 and minus 2 to account for when you have a little left over. Okay. All right, so how do we prove this? Okay. I meant to erase this. That's okay. I'll do it again. Did I erase the wrong? Okay. All right, so we can basically prove this visually. So originally we had one wide red array. That was our input. And we divided into groups of 5. So I've taken each group of 5 and turned it into a column. Okay? And imagine listing each column from smallest to biggest. Okay? Now that means if I arrange the array that way, then the middle row represents all those medians of sets of 5. 2 numbers bigger, 2 numbers smaller. And let's say I also rearrange the rows to go from smallest median to biggest. Rearrange the columns to go from the smallest median to biggest. So at least visually, the median of median shows up in the middle. It's a proof, so we can spend time to do this. Okay. Now I want to argue that, of course, the purple element is bigger than half the green and smaller than half the green. But I want to argue that it's bigger than a lot of red as well, and smaller than a lot of red as well, because that's really what I'm trying to split. Okay? So I've used teal. Teal represents things that are definitely smaller than this median of medians. Okay? So we know that these are definitely smaller. Okay? Because the median of the green row. But I also know that each of those medians are bigger than 2 elements in their set of 5. So I know that these are also smaller. Okay? In the worst case, it's possible that it's bigger than some other guys too. Okay? I guess it's also bigger than these two. I could do the same thing on the bigger side. I know that the pivot is definitely bigger than everything else, the other kind of mini medians. And each of those mini medians was bigger than 2 elements in its set of 5. All right, so kind of how much does that add up to? We have the calculations down here. So if I look at, for example, the yellow, I guess there's n over 5 times 1/2, so it's bigger than at least half of the green. So that's how many are in the green row. And then each of these, gets 3 points. Right? Itself plus the 2 from its set of 5. So overall, we get n over 5 times 1/2 times 3. You get 3n over 10. That it's less than or equal to. Assuming it's a multiple of 5. It's not a multiple of 5, you get plus or minus a little bit. Okay? And same with the other side. It's going to be at least 3n over 10. All right, so we get this. It does work. It'll give us an approximate median. It's actually better than what we assumed before because it's actually getting rid of 30% on one side or the other. The running time, right? I need linear time to do this initial step where I just go through each set of 5 and pick out the middle one. And then down here, I'm finding the median out of n over 5 elements. Okay. So overall, I'm spending n plus tn over 5 time for the subroutine. Yeah.
No, you have to sort it. So you have to sort the B.
No, you don't have to sort B. So I'm recursively finding the median out of B. I'm not sorting B. In the proof, I sorted B just so I can visually show you 3n over 10. Okay, so, all right, so now here's whatever. The only thing about this algorithm is now I'm using this median of median subroutine instead of approximate median. Okay. But otherwise, it's the same idea. I compute the rank of the pivot I get. I divide things. I recurse on the appropriate half. Okay. All right, so what does the running time come down to? All right, so we can model it as n over 5 plus 7n over 10 plus n. Okay, where does that come from? This is coming from the median of medians, where I divided the input by 5 and then I recurse to find the median. Okay. And then it was an approximate median that got rid of, it's either 3n over 10 or 7n over 10 in the worst case. That's what we proved. It's in the middle something. Okay. But I'm always getting rid of 30% of the input. Either getting rid of the bottom 3n over 10 or the top 3n over 10 in the worst case. Here we get luckier. And then we recursively go into that side. So that's where we get 7n over 10. Okay, so a little different from before because we have 2 recursive calls. Okay. Plus linear work. Okay. So maybe here's a good example of that will display the robustness of recursion trees. So, okay, originally I have an input of size n. The total work is about n. Okay. Now I have 2 subproblems, and unlike any example from before, they're different size. So let's just write them out. I have n over 5 here, 7n over 10. The total work on that level comes out to 9n over 10. Okay. All right, let's go further. I have n over 25, 5 squared, plus, oh boy, 7n over 50. Okay. Another 7n over 50. And then 7n over, so 49n over 100. Okay? But if I add them all up, if you kind of think about what we're effectively doing is we're taking the term n over 5 plus 7 over 10 squared, and each of the leaves represents sort of one factor when you expand out the product. You have n over 5 squared, you have 2 n over 5 times, you have 2 1/5 times 7/10, then you have 1 7/10 squared. Okay? So sorry, it shouldn't be n over 5, it should be 1 over 5 times n. Okay, which is 9/10. And now that you see the pattern, we don't even have to add things up explicitly to have some confidence that the next one will be 1/5 plus 7/10 cubed. It's just going to keep going in this fashion. Okay? Now each of those represents 9/10, 1/5 plus 7/10. So I get 1 plus 9/10 plus 9/10 squared plus so forth, all times n. Okay? So what's all that going to add up to? Yeah, I mean, I heard many people say it. All of these 9/10, exactly what we did before, is some constant. And all this added up will give us a big O of n running time. Okay? All right, so that is it. And so next time we'll do Euclidean distance and Fourier transforms.